You have followed every tutorial, you have installed Kali Linux. You have opened the terminal, typed the command exactly as written and hit enter. And then this appears. Error monitor mode not supported. Or maybe your adapter simply doesn't show up at all. Or packet injection fails silently and nothing works the way it's supposed to. Here is what no tutorial tells you. That error has nothing to do with your commands. It has nothing to do with your knowledge, your Linux installation, or anything you did wrong. It has everything to do with a decision made inside a piece of silicon you probably never thought to question, the chipset inside your Wi-Fi adapter. And once you understand why that decision was made and who fought to reverse it, the entire landscape of wireless security research looks completely different. This is not a story about a product. It is the story of how a scattered community of researchers, developers, and open-source contributors built an entire ecosystem that the hardware industry refused to build for them, and how one small adapter from a Taiwanese manufacturer accidentally became the symbol of everything they achieved. If you want to understand wireless security at the level that actually matters, stay with this. Because by the time we're done, you won't need anyone to hand you a recommendation. You'll be able to evaluate any adapter yourself, and you'll understand exactly why most of them are useless for this work before you even plug them in. And if that kind of deep technical clarity is what you're here for, subscribing now means you won't miss what's coming next. Because this story goes significantly deeper than one adapter. Let's start with what Wi-Fi actually is at the level most people never see. When your laptop connects to a router, your Wi-Fi adapter operates in what's called managed mode. In managed mode, the adapter behaves like a polite guest at a party. It only listens to conversations directed at it. It only speaks when spoken to. Everything else, every packet flying through the air from every other device on that channel, gets filtered out by the driver before it ever reaches your operating system. This is by design. For normal users, that filtering is exactly what you want. It reduces noise, improves performance, and keeps the network stack clean. But for a security researcher, that filtering is catastrophic. Wireless security testing requires seeing everything, every beacon frame from every access point, every probe request from every device searching for a network, every authentication handshake between a client and a router, even if that handshake has nothing to do with you. You need to observe the raw wireless medium, not the curated slice your adapter decides is relevant. That capability has a name. It's called monitor mode. In monitor mode, the adapter stops being a selective listener and becomes a passive recorder of everything on the channel. No filtering, no association required. Raw 802.11 frames exactly as they travel through the air, delivered directly to the application waiting for them. And then there is packet injection, which goes one step further. Injection is the ability to craft an arbitrary 802.11 frame from scratch and transmit it onto the wireless medium, as if it originated from any device the researcher specifies. This is what makes deauthentication attacks possible. It's what allows a researcher to force a WPA2 handshake to occur so it can be captured and analyzed. It's the mechanism behind a significant portion of the wireless attack techniques that penetration testers use every day. Monitor mode and packet injection together are the foundation of wireless security research. Without them, you are not doing wireless security testing, you are watching a wall. So the question is obvious: why don't all Wi-Fi adapters support them? The answer is not what most people expect. The common assumption is that certain adapters have special hardware that enables these features, that you're paying for extra capability when you buy a research-grade adapter. That assumption is almost entirely wrong. Think of it this way. Imagine a camera with a high-quality sensor that captures full raw image data, every photon, every gradient, every detail the sensor can record. But the manufacturer ships that camera with firmware that automatically converts every image to JPEG before you can access it. The sensor is fully capable of delivering the raw data. The firmware intercepts it, compresses it, discards what it considers unnecessary, and hands you a processed result. Now imagine a third-party firmware replacement that disables that automatic conversion and gives you direct access to what the sensor actually captured. That firmware didn't add any hardware capability. The sensor could always do this. The firmware simply removed an artificial restriction. Monitor mode is the raw format of Wi-Fi, and most consumer adapters ship with the firmware equivalent of mandatory JPEG conversion baked in. The physical radio hardware in most Wi-Fi chipsets is capable of receiving all 802.11 frames on a given channel. The silicon doesn't inherently discriminate. What discriminates is the driver, the software layer that sits between the hardware and your operating system. The driver implements the filtering. The driver enforces the association state machine. The driver decides what reaches your applications and what gets discarded. Supporting monitor mode means writing a driver that can bypass that filtering on command. Supporting packet injection means writing a driver that allows arbitrary frame construction without the normal association and authentication process getting in the way. Manufacturers don't do this, not because the hardware prevents it, but because there is no commercial reason to support it. Consumer Wi-Fi is sold to connect to networks. The expected behavior is a connected client following the 802.11 protocol politely. A driver that lets you shatter that protocol and operate outside its rules serves no consumer use case that a manufacturer wants to advertise. So they don't build it, and in many cases their firmware actively prevents it. This is where the story gets interesting, because the security research community needed these capabilities, and the hardware industry wasn't going to provide them. So the community had to build the solution themselves, starting with whatever hardware gave them a foothold. In the early 2000s, that foothold came from an unexpected direction. Atheros Communications was a chipset manufacturer focused primarily on the enterprise Wi-Fi market. For regulatory compliance and commercial partnership reasons, Atheros made an unusual decision for the era. They released reference driver code for their chipsets as open source. They weren't trying to enable security research. They were trying to make their chips attractive to Linux-based embedded hardware vendors who needed driver access to build their products. The security research community noticed almost immediately. Because the Atheros driver code was open and documented, it was possible to study exactly how the driver managed the relationship between hardware and operating system. Developers could find the filtering logic. They could locate the association state machine. And critically, they could modify the driver to expose what the hardware was actually capable of doing. The Atheros AR9271 chipset became the foundation of an entire generation of research-grade Wi-Fi tools. It wasn't the fastest chipset available. It wasn't the newest. But it was documented, open, and modifiable in ways that most of its competitors were not, and that made it uniquely powerful for the community's purposes. Around the same time, a tool called Aircrack-ng was taking shape. Originally derived from earlier wireless auditing tools, Aircrack-ng was becoming the standard suite for wireless security testing, WP cracking, WPA2 handshake capture, packet injection, network discovery. The tool was technically sophisticated and actively maintained, but it was only as useful as the hardware beneath it. The primary maintainer of Aircrack-ng, Thomas Dautrep de Bouvet, known in the community as Mr. X, understood this dependency completely. The tool required hardware that could actually deliver raw frames and accept injected ones. The Atheros-based adapters could, most other adapters could not. The community began converging on Atheros hardware by necessity, and one manufacturer was paying attention. Alpha Network is a Taiwanese company that was not, at the time, a household name in security circles. They made USB Wi-Fi adapters for a range of commercial applications, including long-range wireless connectivity for environments where standard adapters couldn't reach. Their hardware was built around chipsets chosen for range and sensitivity rather than speed. Characteristics that, as it turned out, were also extremely useful for wireless security research that required picking up distant access points and client devices. Alpha began manufacturing adapters around the Atheros AR9271 chipset. The combination was nearly accidental in its perfection. High-gain antennas, a chipset with documented open-source drivers, USB connectivity that worked across Linux distributions, and a price point that didn't require a corporate budget. The community adopted it, tutorials were written for it, courses were built around it, forum posts recommended it. And as each generation of Aircrack-ng users learned wireless security on Alpha hardware, they passed that recommendation to the next generation, not because the brand had earned some abstract loyalty, but because the hardware reliably did what everything else refused to do. Here is where it's worth pausing to correct something that causes real confusion. The Alpha brand does not guarantee compatibility. The brand is an entry point into a conversation that needs to happen at the chipset level. Alpha has shipped multiple product lines over the years using different chipsets, and not all of those chipsets have equivalent driver support. A different hardware revision of what appears to be the same adapter model may contain a completely different chipset inside, and that chipset may have significantly weaker support for monitor mode and injection under current Linux kernels. The adapter on the outside is almost irrelevant. What matters is the chipset inside, and the only reliable way to know what chipset you have is to identify it directly. If you run LSUSB in a Linux terminal with the adapter plugged in, you'll see a USB vendor ID and product ID. Those IDs can be cross-referenced against the Linux USB ID database to identify the exact chipset. From there you can check the community driver support tables to understand what that chipset is actually capable of, and whether a maintained driver exists that supports research features under your current kernel version. That is the skill. That is what stays relevant regardless of which specific adapters are currently available or which product line's alpha happens to be shipping this year. Which brings us to the second major chapter of this story and the conflict that is still unresolved today. If Atheros represented the open-source golden era of wireless research hardware, Realtek represented something considerably more complicated. Realtek Semiconductor is one of the largest chipset manufacturers in the world. Their Wi-Fi chips appear in an enormous range of consumer devices, routers, laptops, USB adapters across dozens of brands. And unlike the early Atheros situation, Realtek does release Linux drivers, official ones maintained by the company submitted through the standard kernel processes. This sounds like it should be better, it is frequently worse. Realtek's official Linux drivers are written for mainstream consumer compatibility. They implement standard managed mode operation cleanly. They connect to networks reliably, but their treatment of monitor mode and packet injection support has been inconsistent at best and actively hostile at worst. Official driver updates have repeatedly broken monitor mode functionality across kernel versions. Features that work correctly under one kernel release would fail silently or produce incorrect behavior after an update. The injection implementation in official Realtek drivers has been buggy in ways that matter enormously for security research: frame corruption, timing errors, incomplete support for the frame types that wireless testing tools depend on. The community responded the only way it could. Independent developers forked the official Realtek drivers, maintained separate branches, and added the research-grade functionality that the official releases neglected. The Aircrack-ng/RTL 8812.0 repository on GitHub became one of the most referenced sources for a maintained, research-capable driver for the RTL 8812AU chipset, one of the most widely used chipsets in current-generation alpha adapters and other research-oriented hardware. This creates a situation with no clean resolution. The official driver exists but breaks research features. The community fork works but requires manual installation, doesn't update automatically with the kernel, and depends on volunteer maintainers who have no obligation to continue. Every major kernel version is a potential breaking point that someone in the community has to identify, diagnose, and patch. This is the unglamorous reality beneath the polished tutorials and the adapter recommendations. The ecosystem that made wireless security research accessible wasn't built by companies with engineering teams and product roadmaps. It was built in spare hours on personal hardware, by people who needed the tool to exist and were willing to build it themselves. And right now, that ecosystem is facing a transition it may not be fully prepared for. Wi-Fi 6, the 802.11 AX standard, represents the largest architectural change to the 802.11 protocol in more than a decade. The physical layer is more complex. The multi-user scheduling mechanisms are more sophisticated. The chipsets implementing it are newer, less documented, and in most cases have not yet developed the mature open-source driver ecosystems that the 802.11n and 802.11ac generations eventually produced. For security researchers, this creates a significant gap. The tools that currently dominate wireless security testing, Aircrack-ng HCX tools, the broader ecosystem of monitor mode-dependent utilities, were built around the frame structures and chipset behaviors of the previous generation. Adapting them to Wi-Fi 6 is not a simple update. It requires driver development work at a level of technical depth that the community does not have unlimited capacity to absorb. The adapters that work reliably for wireless security research today are largely still 802.11ac devices, not because 802.11ac is more relevant to modern networks, but because that's where the driver maturity currently exists. The community that built the previous generation's research infrastructure took a decade of work to achieve what it achieved. The Wi-Fi 6 transition is happening faster than that timeline allows, and the manufacturers whose chipsets would need to be the foundation of the next generation have given no particular indication that they are interested in supporting the use case that would require it. So here is where everything lands. The Wi-Fi adapter question that every beginner asks is not actually a shopping question. It is a systems question, a question about the relationship between hardware capability, firmware constraints, driver architecture, and community maintenance. The adapter is the visible surface of a much deeper technical and human story. Monitor mode is possible because certain chipsets were documented openly enough that the driver layer could be written to expose it. Packet injection works because developers were willing to reverse engineer the 802.11 association state machine and find the points where arbitrary frames could be inserted. The alpha adapter became the community standard not because it was designed for security research, but because it combined the right chipset with the right form factor at the right price, and because the community decided to make it work and then taught everyone who followed. The framework for evaluating any adapter is now yours. Identify the chipset using LSUSB, cross-reference the USB vendor and product ID against the Linux USB ID database, check community driver repositories for maintained support under your kernel version, and test monitor mode and injection directly rather than assuming the adapter's marketing is accurate. The adapter is a key, the chipset is the lock, the driver is who cut the key. And right now, for the next generation of wireless standards, someone still needs to do that cutting. Whether manufacturers will ever treat this as a responsibility rather than an inconvenience is a question worth sitting with. The hardware capability exists in most modern chipsets. The firmware restrictions that prevent security research use are design choices, not physical limitations. The argument that removing those restrictions creates security risk runs directly into the argument that the researchers who need them are the ones defending against the attackers who find other ways to achieve the same result anyway. There is no clean answer, but it is exactly the kind of question that determines whether the next generation of wireless security researchers will have the tools they need or will spend the next decade rebuilding what this generation built from scratch for hardware the industry still didn't design for them. If that question stays with you, leave your answer in the comments. The conversation there tends to be as interesting as anything in the video itself. And if you want to follow what happens next with Wi-Fi 6 driver development and the tools being built around it, subscribing means you'll be here when that story develops enough to tell properly. The next chapter isn't finished yet, but it's already being written one commit at a time.